Netcasts you love.
From people you trust.
This is TWiT.
Bandwidth for TWiT Specials is provided by CacheFly at CACHEFLY.com.
A man sits in his car in Los Angeles traffic an hour late for his meeting. Now, this in and of itself isn't that interesting. It happens all the time. It's a common occurrence in Los Angeles. But when it becomes interesting is when that man is Elon Musk. Because Elon Musk doesn't just complain about the problems of the world, he looks for a way to fix them. And that was the birth of the Hyperloop. A Hyperloop competition brought together competitors from around the world to dream up of the next generation high-speed, high-capacity public transportation system. A pod suspended by electromagnetics, propelled through a vacuum tube. Well, that's why we're here in Menlo Park, California, speaking with the guys from rLoop, the future of high-speed transportation. I'm standing next to the lead engineer for Team rLoop, Thomas Lembeau. He's the man who brings together the disparate talents that are needed for the rLoop effort. Thomas, what's different about rLoop? We know that you're the only non-school entry allowed onto the track that has advanced into this stage of the competition. But it's not just that you're not attached to a university, it's the fact that you are really an open source organization. What does that mean?
We have people from all around the world. We don't have any doors per se. Anyone can come in. We have people that are in high school. We have people who are retired. We have people who are jobless or students. We have CEOs of companies. So we are really open to everybody. So anybody can join. They can bring their piece to the puzzle and try to help us with our task of building the Hyperloop.
Oh, that is revolutionary in and of itself, because if you look at all the other entries, either related to universities or being supported by large corporations, it's sort of the traditional structure. You earn your bones, you get your education, you get your degree, then you come in and they tell you what you're going to work on. It sounds to me, with literally hundreds of people who have been part of your team, who are active with your team, you sort of say, well, what can you do? Yeah, we need that. Go ahead and come on board.
Yeah, we take a totally different approach. Instead of assigning tasks to people assign the task to themselves. So the way we do it is we have a core team behind that is basically breaking down the whole structure of how the Hyperloop, what it's made of, and break down that into very, very small tasks, micro tasks. And people join and they see those micro tasks and they say, oh, I think I can do that part. They don't have to understand the rest of the design per se. They have to understand some of it, but they can just pick that thing and do it. And that's the way we've been approaching the thing. It's like, if you join in, if you think you can help anyway, look at what we have and feel free to participate.
Oh, we've been touring around your facility, which by the way, is fantastically provided to you by TE, a company here in the Bay Area. Mm-hmm. And we can see behind us this wonderful board of how your system is going to be integrated. And I can't help but look at this and say, this is really expensive. I mean, we're talking about thousands upon tens of thousands of dollars worth of equipment, sensors, motors, the hover engines. How exactly is that being funded? You're a nonprofit. You don't have big corporate backing. So how do you pay for all of this?
So we pay for that the same way we build this thing, which is crowdsourcing. We had a crowdfunding campaign where we fully raised more than 60,000 on Indiegogo. We have some private sponsors, including TE Technology and Soylent, who are our main sponsor. And we are taking also the approach, we are in the heart of the Silicon Valley. We're taking the DIY approach, garage-style approach, where let's not reinvent the wheels. Let's not make expensive things. There are a lot of things out there that are off the shelf that really do a pretty good job. It's just a matter of tuning them, putting them with the right other parts, and finding cheap ways to do it, but yet a robust, reliable, and that can do the job.
All right, let's talk a little bit about the cheap way of doing it, because, of course, there are people who say that this is a moonshot. This is something like the Apollo program, but for public transportation, which it is in that it's exciting and it's energizing the engineering community. But at the same time, unlike the Apollo program, the technologies that you're using are here. You're combining them. You're bringing together expertise who understands how to use electromagnets, who knows how to use controllers and sensors that can keep you within the tolerances that you need to be on the rails. So what would you say is the bleeding edge? What's the part of the program that most challenges you, that most challenges your team?
It's a tough question. It's the novelty of the whole team is already something. We got very lucky because everything kind of came together organically, and we didn't really expect that. But the most challenging thing is really to just make all the things, all the parts work together and have them within the tolerances. Will it be of weight? Will it be in acceleration that they can handle, and volume and package? That's the thing. But again, we don't have to reinvent the wheel. Everything exists. And I think rLoop kind of took the same approach, the way they are organized, to the way we build a thing, which is rLoop took a bunch of software and way that our things exist, Slack, Google Drive, Google Hangout, Jira. We're using all those things together to organize our team. And we're doing exactly the same for the rLoop, so Hyperloop pod, which is what do we have right now that exists that can do the job correctly. And the challenge has just been to put them together and finding the right way to put it together. But just because we had so many people looking at the project, it's you can find thousands of approach for everything. You just have to pick the right one in the end and make sure to take the right executive decision for, okay, this is the way we're going to go.
It's a fascinating story, and I think now we need to take a look at some of the subsystems and the engineers who are heading up the different divisions of the rLoop effort. An effort like rLoop is based on a team, and a team doesn't just come together, which is why I'm speaking with Dante Bretano, who's going to explain how rLoop came to be. Dante, again, rLoop is a different kind of organization. It has a leader, but no one's getting paid. Everyone's a volunteer, and everyone brings the skills that they have. Tell me a little bit about that. Why did you decide to form this open source nonprofit organization?
You know, at the beginning, it was the only way we could have operated. We needed expertise, and expertise lives all around the world. It's not just in the Bay Area. It's not just in California, United States. People around the world needed to be able to contribute and help build the project. So that's kind of how we got into that mode. It was mostly out of necessity. Thanks to amazing tools like Slack and, of course, Google Hangouts and all sorts of collaboration tools, we're able to keep everybody on the same page, keep everybody up to speed. One of the other things is, because it is volunteer, not everybody who would be perfect for the job can volunteer. So there's some times where you might have 100 experts, but all of them have 80-hour-a-week jobs. So you need to be able to pull talent from where it comes from.
As a true global organization, really one that pulls talent from every time zone, every part of the planet, isn't it difficult for you to stay on time, on schedule? I mean, because ultimately it is a competition. You do have a deadline. You do have to get a product onto the track. Doesn't this make scheduling difficult?
It definitely does. One thing that I think is very unique to us is that companies pool talent. We're kind of amassing talent. People are coming to us. We're not reaching from them. So the motivation's a lot different. It's not for a paycheck. It's for lack of a better term, changing the world, for lack of a better trope to use. So it's more something that people want to come to. It's not so much of a job for people. It's their weekend project. It's what they do to get away from their day job. So people's motivations, people are very internally motivated here, and you're able to not have to really worry about deadlines and such, because everybody is so focused on getting things done that there's really no reason not to throw your heart into it.
It's not a job, it's a passion. And whenever you can get people together for a passion rather than a paycheck, something magical happens. Now, let's talk a little bit about that magical, because I heard an interesting story this morning as we were touring the halls, and that was about an Uber driver who joined the rLoop team. How did that come about?
So that was a very interesting story. Probably my favorite story about rLoop so far. What happened was, one of our team members was coming from San Francisco, came down here, took an Uber, and he's going down there, making conversation, and the Uber driver's like, "Hey, what are you going to this business parkway for on a Sunday? You work on Sundays?" Like, "Oh, no, we're doing this thing, rLoop, and the driver was interested. He's asking more questions. Turns out that, at the time, we were having a pretty big issue with our battery system, and we're trying to find the right expertise to get the batteries done properly. So anyway, back to the driver. So he's driving down, and They're talking. Turns out that the Uber driver actually just retired from Tesla as a battery engineer, and he was driving Uber just to stay busy, in his retirement. So he was super thrilled with the project. He didn't know it was even local. So he knew of rLoop and was following the story, but he didn't know that it was in his backyard. So that day he just signed out of Uber and came inside with our team member that he was driving, and he's been here ever since.
Dante, I want to switch gears really quickly and talk a little bit about the facility that we find ourselves in right now. Actually all of the other entries have a lot of money behind them. They've got corporate sponsorship, they've got university money, they've got staff and professors who are pretty much experts in everything that they might need. Again, since rLoop is more of a come-as-you-are organization, it's always been difficult to do machining. It's always difficult to find a way to create the pieces and parts that you need. Thankfully, you had TE, who had this wonderful workspace. They invited you in, and they've given you access to all this machinery. How much has that been a key in your effort?
It's been absolutely key. We lucked out with TE. They have, as you can see, tons of equipment around us, lots of crazy expensive machines that we would never have access to. We could have always gone the makerspace route, which was actually our primary option. That was what we planned on doing and getting a warehouse space. But TE was nice enough to let us come here, use their machines, and give us some of their experts as well. So there are some people from TE who, out of their own fruition, came down and help out.
Dante, thank you very much for speaking with us. Thank you for sharing the story of rLoop. It is always nice to see an organization that has really become sort of the Burning Man of the Hyperloop competition. And we'll get back to the rLoop offices and the technology that they're creating to build the next generation of public transportation. With the Hyperloop being such a futuristic concept, it's no surprise that you need some pretty sophisticated software to make it work, which is why we're speaking with Paul from the rLoop effort, who's going to explain to us how they keep their pod on track. Paul, the rLoop entry actually has two different control systems. Why is that?
Right, yes. So we have a real-time control system and a non-real-time system. The non-real-time system takes care of communication and communication with the ground station and updating software. So for example, if we need to update our algorithms or fix bugs or anything that might come up, we can do that remotely using this non-real-time system. Now the real-time system, it handles all of our stability and control algorithms, and those run in real time. And that means that that there's no operating system that might cause any timing issues or any performance bottlenecks that might cause the system to malfunction.
And that absolutely makes sense, because when you're talking about the non-real-time control systems, maybe syncing up with the ground station, you can take a little bit of lag. I mean, you can have an operating system there to make sure that you get the features that you need, because it's not as time sensitive as the real-time control systems that are, say, controlling the gimbaled hover engines. If those lag, you crash. Now, you need to keep this craft within 1 degree of its true path. Otherwise, you'll actually hit the rail. What sensors, what software do you use to try to make sure that this is going to stay within that margin of error?
Right, so we have a number of sensors, distance sensors, which measure the distance from the rail. And using that, we can use the, we have wheels that touch. They essentially touch the rail, and we can use that to ensure that the pod is in the right orientation, pointing in the right direction.
Now let's get really nerdy. We've got a pretty advanced audience, and a lot of them do their own software development, their own hardware development. What is your language of choice? What are the devices that you're actually using to talk to, say, the controllers and the speed controllers? And how many members do you have on your team?
Okay, so we use Teensies and Raspberry Pis. So the code running on the Raspberry Pi, I think it varies. We use a bit of C, and we also use Python quite a lot. Python's very useful for communication, for rapid prototyping mostly, and because it's non-real time, we can afford to use it and we can afford to use it in the non-real-time side of things. For the real-time side of the system, we use C++ on the teen Cs. So that allows us to have the performance that we need to run these algorithms.
I think that's actually a good lesson for our audience who may be wondering when you use different devices. We do a lot of projects on our network, and people are saying, well, why wouldn't you do that with a Raspberry Pi, or why wouldn't you do that with an Arduino? And talking to them about an embedded system versus a system with an OS, well, it really becomes important when you talk about a transportation system like the rLoop. Last question. As you're looking down the line, because again, you are coming close to a deadline here, end of October, this has to be on the track, it has to be competing. What do you see as the big software challenges? What keeps you up at night?
Right. So personally, the thing that keeps me up at night is the fact that we have a number of nodes, what we call nodes, which are essentially a Raspberry Pi and a Teensy together, and these nodes each have their own job. They each have their own purpose, and they have to communicate together. And for that, we use a CAN bus, which is a method of communication between various bits of hardware, which is used in the auto industry. And so that bit is what I find interesting, and it means we have to make sure that the nodes are in sync, they can communicate properly. So that's the bit that I'm...
And of course, since you are using the control area network, we might need to talk to Chris Miller and Charlie Valasek, who hacked that Jeep Cherokee not too long ago using the CAN bus. Paul, thank you so very much. Really, seeing your team is inspiring. Seeing that you've brought together all these people it's enjoyable. Just to see them come together for a shared passion for creating something new. Is there anything that you want to plug? Is there a project that you're working on? Is there a Twitter address you want to send people to if they want to find out more about your work in the real world?
Unfortunately, no. I wish, but no, unfortunately.
All right, thank you again for your time. Thank you for your effort with the rLoop. And folks, that's how you do software development. One of the key features of any Hyperloop project is efficiency, the ability to transport long distances with a far less reserve of energy than you would with traditional transportation, which is why the rLoop team is using hover engines. I'm speaking with Amir, who's going to explain how hover engines work. Amir, when you turn this on, I see something that looks like a quadcopter motor. It just spins really fast. Of course, it doesn't have a propeller. It just creates a magnetic field. In fact, multiple magnetic fields. How does this keep the craft from touching the ground?
So, hover engine is just basically magnets, rare earth neodymium magnets arranged in a special orientation called Hallback array. So every magnet is arranged next to another, and the magnetic field of both magnets are at 90 degrees. So when the engine spins up, it creates eddy currents into this subtract, and those eddy currents create a secondary magnetic field. So in essence, that magnetic field, by Lenz's law, opposes the way it was generated. So that in turn creates two kinds of forces. So, and both of them are mutually perpendicular to each other. So one of them is the lift force, which is higher in magnitude. One of them is the drag force. Since these are arranged in a Hallback array, so the drag force is very small compared to the lift force. So that lift force allows us to levitate above the surface. So these engines have a nominal load capacity of about 45 kilograms. And the maximum they can take is 68 kilograms. So if you want to have efficiency out of these engines, you would match a weight between 40 to 50 kilograms. But if you're using them to full potential, you can go up to 60 kilograms as well. These engines are really good. We are using 8 of them. 4 of them are gimbal. So the 4 engines which are fixed are going to provide straight levitation. Another 4 of them can gimbal and provide propulsion and braking. So this is like, the hover engine which we bought from Oxpax.
That's one of the unique features of the rLoop effort, the fact that you're using 8 levitating engines, and 2 of which are on gimbal, so they can be moved, which means that your craft can actually provide a little bit of its own propulsion. Not as much as, say, the pusher device that we're going to be using at the Hyperloop competition, but enough to at least help you steer and stay on track. There are a few other interesting notes about these hover engines. The first is that it has to be a non-ferrous surface. So if it's iron, it just sticks. It's a magnetic field. The second thing is it has to be conductive. So it's a non-ferrous conductive surface. That's what allows the magnetic field, the eddy currents from the hover engine, to actually create a magnetic field within that surface. Is this what the track is going to be made of? It's going to be made out of copper, out of aluminum, or whatever.
So the SpaceX track is going to be made out of the same material which we're using now, aluminium 6061. So this is exactly the same material, and it's going to be all the way from the start to the end of the tube, and in between two sheets. So these are 0.5 inches thick, and in between the two sheets we will have a central I-beam that is also going to be made from aluminium, so that we can use that central beam for braking and the shades for levitation.
People are going to be looking at, say, the small scale device, which we've got footage of, and they're going to wonder why the gimbal only goes side to side. In our minds, we think, well, if you want to go forward, you would aim all the hover engines back, and if you want to slow down, you would aim them all forward. But that's not what you have to do when you're dealing with eddy currents. Tell me, how does that work? How do I get forward acceleration, and then how do I get braking?
So it all depends upon, like, if you deep dive into how actually the force works, how the levitation force works, then you will get an idea once, I don't know, if you have seen the reverse thruster in an airplane, the jet engine, how it behaves. They also open up and the air is flowing through, backside of the channel, and it acts as a thrust reverser. So not exactly, but in some way it's similar to the analogy of how, gimbaling this way will provide you braking, and gimbaling this will provide you acceleration. So if you take a look at the magnetic field and the arrangement and how lift force is generated, so it's currently like this, and if you gimbal them somewhat way inside, it's going to provide some braking, and if you move them outward, it's going to provide you some sort of thrust. So the maximum we are gimbaling is plus minus 2 degrees, and it's going to give out 60 newtons of thrust per engine. So about more than 264 newton something.
Let's talk a little bit about the intricacies of this propulsion, because the hover engines are fantastic. I mean, they're wonderful to see in motion, but you need to keep your pod within 1 degree of its intended direction, which means you've got a lot of sensors that can adjust that gimbaling to keep it on the I-beam. Is that really a challenge, or has that part been licked?
So yeah, it's a challenge, and we have solved it for now. But so the hover engine, you have to keep them stable at exactly 90 degrees so that you're not creating any kind of thrust. Because when you're in a low pressure environment, there's nothing resisting that drag, nothing resisting that forward force, which you're getting by just a little bit of tolerance stack up of the engine. So you have to be very, very exact and very, very sure of what you're doing with them. And a lot of teams have been using them. A lot of teams have come up with their own control systems, but we are using distance sensors, we're using laser range finders, we're using accelerometers to keep all the telemetry data inside, in flight computer, feed it into the flight computer, and get a feed of how to control these engines. So the SDK which you have seen is our test bed. So our goal with that is to control that SDK within millimeters of, not exactly millimeters, but like micrometers of accuracy, and then we will unload that software onto the same hover engine. So we have to test and benchmark our software and control systems on the SDK, and then we'll move on to the hover engine.
Amir, one last question, and this is my inner geek screaming out. You mentioned that you're going to be working in a low pressure environment, and anyone who's ever dealt with thermodynamics knows that low pressure environments are really good insulators. That's why we have vacuum thermoses. You're going to be pumping a lot of power through these hover engines. I believe the nominal voltage was 72 volts, and it can pull up to 70 amps on startup. So this is an enormous amount per engine. That translates into heat, so that they're going to warm up, and then you're going to be in a near vacuum. So they're not going to have the convection cooling that they would out in a normal environment. What are you going to do to make sure that these don't melt down on the track?
So thermal systems has been one of the issues with the whole Hyperloop concept as in general, that in, like you said, in low pressure environment, it's hard to get rid of that excess heat which you're generating. And with aluminum, you're going to have see a skin depth effect. So that is that there as well. And with these Howard engines, you're right. So the nominal voltage is input is 50 to 72 volts DC. And it can go up, the current input can go up to 125 amps. So it's going to generate a lot of heat. So to mitigate that, we started with a bunch of different cooling systems. We reviewed different options and came up with liquid CO2 options, because you seriously don't want to go into cryogenics, because anything above liquid CO2 is cryogenics, and that's a whole different level of complexity you are going into. So we avoided that approach, because our approach in here in rLoop is to use the technologies which have already been demonstrated, which are already in use in different scenarios. So we're not really trying to reinvent the wheel. Use whatever we have, and then if there's something that is not out there, then go about doing something about it. So with the heat systems, we tried the liquid CO2 approach, but then we recalculated our trajectory and our analysis, and we came up to a conclusion that the complete run, the complete from A to B of the tube ends, it's going to be about 18 to 20 seconds. And so these engines, we calculated thoroughly that they can be, in a safe zone, not even the, warning zone. They can be even safe zone for about 90 seconds, at 1.5 minutes. So we are pretty much safe with these engines for the flight profile we are aiming, but we do have a backup of cooling system in our mind. So during the first test, we are going to try out our method. If we need a cooling system, we have already designed it, will just need to be implemented. So we've got it covered.
It's basically for a test track, for just a short run, they can deal with the heat buildup. But if we were going into full production, you would definitely need an active cooling system. Last question for our audience, because I know that they're looking at this technology and they are salivating. They look at this and they think hoverboard from Back to the Future, Marty McFly's device. They're not really at the price that we hobbyists could play with. I know in the small model, each of those small hover engines is about $1,000. This is closer to $15,000. When do you think this kind of technology would actually be financially accessible to the backyard maker?
I've been in touch with ArcSpac's engineers over, numbers and datas, and we've shared FEA models and stuff. So in my point of view, they are really working hard on it to make it financially available to every customer. So it's like, if you take example of Tesla Motors, they started with a very high-end model and then they move it down to somewhat accessible to the general public. So the first iteration of this technology is really, really expensive, but I believe that, and it's going to happen in the next iteration, a couple of iteration, it's gonna be available to the general public. So they will do a second version of the hoverboard. So I think not that is going to be financially available, like, very cheap stuff, but like the third and fourth iteration of that hoverboard, it's going to be super cheap, and anyone and everyone can afford it.
Thank you, Amir. Thank you again for speaking with us. And if you are looking at tinkering with the future, it hovers. When people think of the Hyperloop, they think of a futuristic vehicle inside of a near vacuum tube zooming along at 300, 400, 500 miles an hour. But some way, somehow, that pod needs to get onto the rail. And sometimes it's going to need to get off the rail for servicing. That's something that civil engineers know, which is why we're speaking with Matt with the rLoop mechanical team, who has been working on an interesting problem of propelling their pod. Matt, it's not all magnetic propulsion. At some point, the car actually needs to be able to roll on and roll off. What are the unique challenges of trying to do that for the rLoop pod?
Well, you have to figure out a system that doesn't interfere with the main levitation system, like the magnetic that you're talking about. And you need to have something that will support the whole weight of the pod and be able to be used at a very quick notice. So those are the main issues, I would say, or the main challenges.
With all of that added gear, doesn't that take away from the efficiency of the system?
It could, but it might just be negligible if we're smart about how we design it. And it's also a necessary system in case we have like a power failure or we need some way to really load it on mechanically onto the rails, because you need a very specific environment for the magnetic system to work.
Let's talk a little bit about that magnetic system, because there's always been talk about, well, what happens when, not if, but when it fails. There will always be a technical glitch. There will always be something that goes wrong. You don't want to destroy the pod, and you definitely don't want to destroy the rail, because these are very expensive pieces of equipment. How does that alternate propulsion come into that safety margin?
So when the magnetic propulsion system is in use, we have the auxiliary propulsion kind of stowed away, almost like a landing gear system you'd see on a plane. And whenever we have a power failure or some sort of a need for this system, an actuator pushes the system down, the wheels down, and it'll be able to support the entire pod and make sure we don't land on our failing magnetic levitation system. So.
All right, our audience is pretty techno savvy, so they're going to want to know as we get to the competition in October, when you actually have to get your integrated vehicle on the rails. So not just the levitation engine, the hover engine, not just the frame, not just the software controller systems, but everything all in one package. How much of that vehicle that we see would be incorporated into the real vehicle? I guess the question I'm asking is, how much of this can you shed once we get to full-scale production?
I really don't know too much about that, to be honest. Being so new, I would imagine we would still need an auxiliary propulsion system. The magnetic levitation, I think, is there to stay. I think we are designing it such that we don't have to shed too much and redesign very much to be able to upscale this to full production. So,
Matt, rLoop is an interesting group in that you have a lot of people who just sort of come in, they donate their time, they donate their experience, and then they'll be off on their way. I understand you've only been with the group for about 3 weeks. Tell me a little bit about yourself. How did you find yourself at rLoop?
Well, I worked on the SpaceX Hyperloop Challenge is a really cool challenge, and Purdue had a team, and that's where I went to school. And so once I graduated, I wanted to stay involved in Hyperloop because it's a really cool thing. And I heard about rLoop, and so I decided I'm so close to this, the headquarters of rLoop, so I might as well get involved some other way. So I decided to come in and get started on that, and I was really impressed with just how organized everything here is, how excited everybody is, how driven everybody is. A lot of people are working 2 jobs, a job on top of this. I consider this a job. So it's just really cool to see the expertise here and all the involvement and the ambition.
I guess the last question would be, what do you foresee for yourself after rLoop? I mean, this is a great example of cooperation among engineers and great minds. But at some point, people will go off into their own directions, and I'm sure you'll find your own. How would you like to leverage this experience into your future?
I want to use this as a mechanical design experience. To be honest, I want to stay involved in Hyperloop as much as I can, specifically rLoop, if we decide to go into a full-scale thing. But I think working in an open source group is a very different and upcoming way of having teams work in a professional environment. And I think that would be really useful for companies in the future. So,
Matt, thank you very much for speaking with us. Thank you for explaining how the auxiliary propulsion system works. And we'll get back to all of our coverage of the rLoop effort for the Hyperloop. For the rLoop, the brains is provided by some very sophisticated software. The brawn is provided by some very expensive hover engines. But the face will be the pod, which is why I'm speaking with Amir, who's going to explain what went into the design of the aeroshell and the pressure vessel in which the rLoop entry has to live. Amir, behind us, we see the beginning of the test scale device. What went into the design? Why did you come up with this design? Why did you come up with this shell?
So I'll start with one thing, that this pressure vessel is exactly as similar to a pressure vessel of a Learjet, because it meets all the air and crashworthiness standards of FAA, and we have put into analysis all the body loads of crashworthiness and airworthiness. So this is like exactly similar to a fuselage of an aircraft. And because the guy who designed this, or Aero and Structures lead, works for a private company which designs business jets, so this is exactly his idea. The reason behind doing a pressure vessel is that we are operating in a low pressure environment, and there are certain things that they don't do so well in a low pressure environment. So we had to make sure that the components we are putting can be functional inside a pressure vessel. And so that's why we came up with the whole pressure vessel idea, to put all the electronics and the batteries and other systems which cannot face the low pressure environment to put into the pressure vessel. So this was the beginning of the pressure vessel, and then we came up with, analysis. We analyze it for FAA standards, and then we put it through some testing. So the basic skeleton is complete. We just have to put the skins on top of it, and before we do that, we have to put all the components inside, put the skins on, and do some leak testing, and we'll see how it behaves.
We've all seen some different variants of what will go into the Hyperloop test track, and everyone has their own special sauce, their own design. But what I've always found interesting is they all look, as you mentioned, like airplanes. They look like aircraft. The fuselages are shaped to look in that position that we think is going to be fast. But you're going to be operating in a near vacuum, a very low pressure environment. So the natural pieces that I would put on an airplane won't work in that. I can't use things like surface effect and ground effect. So could I just make a bullet-looking device and shove it down there? Would that be as effective as any pod that's being created for the competition?
So there's one point. So we're not really operating in vacuum. It's just a low pressure environment. So vacuum is like millitoss of pressure. That is vacuum. Like in space vacuum, things start to disintegrate, outgassing effects happen. So in our case, we are not really operating in a vacuum environment. It just happens to be a low pressure environment. So we are going to see some drag. It's not that it's negligible, but there is going to be some drag. In our case, we have about 100 newtons of drag. So that is quite negligible given to the drags we see on vehicles which are on the road, or trains and anything other than this mode of transportation. We see a bit of drag in there. So the reason behind, I'm not sure. I mean, I have seen a lot of Hyperloop pod designs, but I haven't seen any one which houses a pressure vessel, because I'm not sure why people didn't opt for a pressure vessel, but it's a fairly good reason to go for a pressure vessel, because you're operating in a low pressure environment. And the point that you can make something a bullet shape and shove it through the tube may work. Theoretically it will work, but it's just that you have to have control of that, because you're not really going for aerodynamic surfaces so that you can generate lift and stuff, but you have to be, at least you have to make the nose cone such that it can, direct the force over the pod, and there are no shearing vortices behind the pod. So you have to be careful with that thing, but you really don't need to be so aerodynamic about it. But in our case, like if you see, it's the work in progress, so aeroshell. So this is like the male mold we are building. So it's a styrofoam. We'll put some Bondo, we'll sand it down, cure it, and then make a mold, and then we will do a fiberglass nose cone up from this mold. And from the back of the pod, we are using some carbon fiber straps, and we are not really concerned with the back side of the flow, but for the forward nose cone, we want to be just a fiberglass, and that's it. I mean, this is like what it takes to go through that low pressure environment.
Besides, this is a project of passion, and no one really wants to make an ugly ship. This is something that people want to see. It should look a little futuristic, a little bit sci-fi. Now, let's scale this up. Let's say that rLoop goes into full production with your finished product. What are going to be the challenges for moving from a test vehicle like this to something that could actually hold people and cargo? I mean, of course, you do have the challenge of having regular pressure outside of the Hyperloop, low pressure inside, and then high pressure again inside the cargo vessel. But what else? You've got to fit all of the equipment, all of the components, the hover engines, all the safety equipment, the auxiliary propulsion into one single vehicle, one single pod. In your mind, what will be the big challenge in moving to that stage?
Our structure is pretty solid. It's designed in a way to scale up, so we can scale up our pressure vessel. It's not going to be a challenge. The challenge I see personally is the power. So when you go from this prototype pod to a big pod, you have to have a certain efficient means, like a sustainable means of powering this thing, because in essence, this mode of transportation is supposed to be self-sustainable. So that is one problem we might face. And the other problem is that when you go for full production, system, you have to have a very good cooling system, because in low pressure environment, there's no convection. I mean, there is convection, but it's fairly negligible. So you have to design a system that can withstand that low pressure environment. So these are a couple of challenges. Other than that, all of our systems are designed in mind for them to scale up. So it's just like grabbing them and extruding them in a CAD program. So you can scale up all of majority of the components can be scaled up, but there are certain segments that will need design change to go for a full production system.
Amir, thank you very much. Thank you for sharing your time, especially you're a volunteer just like everyone else, sharing your time, sharing your expertise to create this beautiful vehicle. And maybe the folks out there who really want to be makers, your mechanical know-how might live in a Hyperloop. Thomas, I have to say that this is a fascinating team. But the fact that it's sort of, I'll say hodgepodge, but it's not in a negative fashion. I mean, you really have sort of taken the spirit that Elon Musk wanted to bring into the competition of bringing people together from disparate backgrounds, no matter where they may come from, no matter what their experience might be, as long as they can contribute. And you've turned it into an actual entry, a real entry for the future of transportation. Now, I got to ask, what has to happen between now and the end of October? The time is coming. You're going to be on the track. You're going to be competing. You have a lot of the parts, but you have a lot of work to do between now and then. What do you see as the timeline?
So the timeline for us right now, we are finishing the structure of the whole pod. So all the mechanical parts are coming together. Within the next 2 weeks, we should have all those things nailed down. And then we will have to install all the electrical system, the nodes and so forth. They're testing on the side right now, but they need to be integrated. The last big part that needs to be done will be really the full scale testing of the pod, which means all the components in there, make sure everything fits and everything behaves the way we want to. Those are the big things to do. There is a lot of work, but it's not impossible, and we're really working on it.
Thank you very much for spending time with us. Now, if our audience wanted to find out more about your effort, more about rLoop, if maybe they wanted to dedicate their time and their treasure to creating what you have here, where can they go?
So, two things they can do. They can go to rloop.org, and if you click on team, you have join the team at the bottom. What you'll get if you click on that, you get a form, you fill in, and you'll get an invitation on Slack. And like no obligation, you can just join, see what we're up to, and try to help or not. And if people are local to the Bay Area, we need just more hands to build stuff. I mean, we have people coming, going all the time. We have people traveling, but we can always use more people. We have a good team, pretty good team. It's a very awesome experience in here. You get your rLoop T-shirt, you get some Soylent to work on. It's a great people, great mind. We get we do some stuff outside, some networking on the side also. So really big community, and we need pretty much like electrical engineer, mechanical engineer, people who are good with manufacturing, people are really hands-on. That's really what we're looking for. So feel free to reach out. Contact at rloop.org, send an email, and be happy to get you on board.
Thomas, thank you. Thank you so very much for your time. And again, thank you for sharing your vision. And folks, if you've always complained about the state of the world, if you want to make it better, rLoop's giving you a chance to get your hands on the future of transportation.